Hello, Math 200 students. Welcome to Chapter 7. Chapter 7 is about hypothesis testing, introducing us to that. Throughout the remainder of this text, you will study an important technique in inferential statistics called hypothesis testing. A hypothesis test is a process that uses sample statistics to test a claim about the value of a population parameter. So, it tests a claim about some population characteristic, like the weight of all male college students. Someone claims that the average weight is 160 pounds, and then there's a way to test that by taking a sample, and then you can decide whether that claim is an okay claim or not. Researchers in the field such as medicine, psychology, and business rely on hypothesis testing to make informed decisions about new medicines, treatments, and marketing strategies. For instance, consider a manufacturer that advertises its new hybrid car has a mean gas mileage of 50 miles per gallon. If you suspect that the mean mileage is not 50 miles per gallon, how could you show that the advertisement is false? Obviously, you cannot test all vehicles, but you can still make a reasonable decision about the mean gas mileage by taking a random sample from the population of vehicles and measuring the mileage of each. If the sample mean differs enough from the advertisement's mean, you can decide that the advertisement is wrong. For instance, to test that the mean gas mileage of all hybrid vehicles of this type is mu equals 50 miles per gallon, you take a random sample of 30 vehicles and measure the mileage of each. You obtain a sample mean of x bar equals 47 miles per gallon, with a sample standard deviation of s equals 5.5 miles per gallon. Does this indicate that the manufacturer's advertisement is false? To decide, you do something very unusual. You assume that the advertisement is correct. Okay, that's one of the interesting things about hypothesis testing is you first make the assumption that the claim is true. In this case, that is, you assume that mu equals 50. Then you examine the sampling distribution of sample means with n equals 30, taken from a population in which mu equals 50 and sigma equals 5.5. From the central limit theorem, you know this sampling distribution is normal, with a mean of 50 and a standard error of 5.5 over the square root of 30, which is 1. In the figure below, notice that the sample mean of x bar equals 47 miles per gallon is highly unlikely. It is about 3 standard errors from the claimed mean. Using the techniques you studied in Chapter 5, you can determine that if the advertisement is true, then the probability of obtaining a sample mean of 47 or less is about 0.0013. This is an unusual event. Your assumption that the company's advertisement is correct has led you to an improbable result. So, either you had a very unusual sample, or the advertisement is most likely false. The logical conclusion is that the advertisement is probably false. All right, that was probably very hard to follow. Hopefully, as we get into this chapter, you'll become more comfortable with what we just said. Let me see if I can explain that one more time, maybe a little more clearly. The claim is 50. So you just say, okay, if that's true, all right, I'm going to just pretend it's true for a minute. I'm going to take a sample. So the sample is 30 cars in the sample. The mean of that sample was 50. The mean of that sample was 47. The standard deviation of that sample was 5.5. But then you know that the standard error with the distribution of sample means, sampling distribution of sample means, you don't just use the standard deviation of your sample, you divide it by the square root of the sample size. And so, in that case, the standard error or standard deviation of the sampling distribution of sample means is not 5.5, it's actually close to 1. Okay, so that means, assuming the real value is 50, and assuming a standard deviation of 1, this is what that would look like. This is what that distribution would look like. And so then we put what we got from our sample right here, and we say, how likely is it that we would get something like this, or something even more extreme than this, if this were a true sample? If these things were true, what is the probability that I would get something as far away from that value as 47? And when you do your math on that in the calculator, you get that the probability is just 0.0013. In fact, we can do it in the calculator right now. We're trying to find the probability that we get something as far away from this mean as we did, 47 or less. All right, so we're going to go to our calculator. We're going to go second distributions. We're going to go normal CDF, option 2 there. The lower limit, if I am in this part of the graph, the lower limit is anything less than 47, so negative infinity. The lower limit will be negative 1e99. The upper limit will be that value right there, 47. 47. The mean is what they claim, which is 50. The standard deviation is the standard deviation of my sample, which is 5.5, divided by the square root of the sample size, which in this case was 30. And then you click paste, and we find out it's 0.0014. All right, which is pretty close to what this book is saying as well. And again, that means it's only basically a 0.1% chance that we would have gotten that value for our sample if their claim was true, which means we should reject that claim. It's extremely unlikely that that claim could be true based on that probability. Moving to the next page. Stating a hypothesis. A statement about a population parameter is called a statistical hypothesis. To test a population parameter, you should carefully state a pair of hypotheses, one that represents the claim and the other is complement. When one of these hypotheses is false, the other must be true. Either hypothesis, the null hypothesis or the alternative hypothesis, may represent the original claim. The null hypothesis, H0, is a statistical hypothesis that contains a statement of equality such as less than or equal to, or greater than or equal to. The alternative hypothesis, HA, is the complement of the null hypothesis, and it is a statement that must be true if H0 is false. And it contains a statement of strict inequality such as greater than, not equal to, or less than. The symbol H sub 0 is read as H sub 0 or H0, and H sub A is read as H sub A, or I just call it HA sometimes. To write the null and alternative hypotheses, translate the claim made about the population parameter from a verbal statement to a mathematical statement, then write its complement. For instance, if the claim value is k and the population parameter is mu, then some possible pairs of null and alternative hypotheses are, okay, it could be, so like let's just go back to our gas mileage example. The claim is that mu equals 50. So H0 would be mu equals 50. Then the alternative to that would be the opposite of that. Mu does not equal 50. Okay? The claim doesn't always have to be just equals. It could be is greater than or equal to, or less than or equal to. In other words, they could say at least 50. Maybe they say the gas mileage in this car, the mean gas mileage of these cars is at least 50. Then H0 would be mu is greater than or equal to 50. And so HA would be the opposite of that, which is mu is less than 50. Or maybe somebody might say the average grams of fat in this slab of bacon is at most 5 grams. So then mu would be less than or equal to 5. And the alternative hypothesis would be the opposite of that, which is mu is greater than 5. Regardless of which of these three pairs of hypotheses you use, you always assume mu equals k and examine the sampling distribution on the basis of this assumption. Within this sampling distribution, you will determine whether or not a sample statistic is unusual. The table shows the relationship between possible verbal statements about the parameter mu and the corresponding null and alternative hypotheses. Similar statements can be made to test other population parameters, so it doesn't just have to be mu that we're testing. It could be a claim that there's a proportion. The proportion might be 80% of people like bacon, so that would be a P instead of a mu. Or the claim might be the standard deviation of golf shots, of the distance from the center with this golf ball is such and such, and that then we'd be talking about sigma or sigma squared. Okay, so you can read that chart if you want to. Moving on. Example 1, stating the null and alternative hypotheses. Write the claim as a mathematical statement. State the null and alternative hypotheses and identify which represents the claim. So number 1, a school publicizes that the proportion of its students who are involved in at least one curricular activity is 61%. So it would be P equals 61%, or P equals 0.61. That would be the claim. Since it's a proportion, we're saying P, not mu. So the alternative would be the opposite of that. So if P is 0.61, or P is 61%, then the alternative would be P does not equal 0.61. All right, let's read number 2. A car dealership announces that the mean time for an oil change is less than 15 minutes. All right, so this time the claim is mu is less than 15. Okay, we have to make that the alternative hypothesis because it doesn't have an equal to in it. The H0, the original hypothesis, has to have some sort of equality in it, whether it's equal to or greater than or equal to or less than or equal to. But since it says less than 15 minutes, it doesn't say less than or equal to 15 minutes. It doesn't say at most 15 minutes. We have to say that the claim is mu is less than 15. And so since it doesn't have an equality anywhere in that, we have to make that the alternative hypothesis. So it's possible that you can make the alternative hypothesis be the claim. And so then you would make the null hypothesis, H0, be the opposite of that. So if HA is mu is less than 15, then H0 would be mu is greater than or equal to 15. All right, number 3. A company advertises that the mean life of its furnaces is more than 18 years. So again, we have to say here, mu is greater than 18. That's the claim. And since it doesn't have an equality in it, that's got to be the alternative hypothesis. So mu is greater than 18 is the HA. And so H0 would be the opposite of that, which is mu is less than or equal to 18. Moving on. Types of errors and level of significance. No matter which hypothesis represents the claim, you always begin a hypothesis test by assuming that the equality condition in the null hypothesis is true. So when you perform a hypothesis test, you make one of two decisions. Either number 1, you will either reject the null hypothesis, or number 2, you will fail to reject the null hypothesis. That is really important wording, and I need you to concentrate on that wording, okay? This is something students always struggle with over and over again every quarter. And that is this. Again, you either reject it or you fail to reject it. Students want to say, wrongly, you either reject it or you accept it. That's not right. It's not reject or accept. It's reject or fail to reject. To fail to reject is not the same thing as accept. Think of it this way. Somebody asks you to marry them, and you think they might be okay, but you haven't gotten to know them good enough yet, and so you say, well, I'm not going to say no. I'm not telling you no, I would never marry you, but I'm going to say I'm not ready to accept that proposal yet. So you're not rejecting them, but you're also not accepting them. You're just failing to reject it. So it's like you are reserving judgment. You are postponing the full judgment yet. You're just saying, I'm not accepting it, but I'm also not going to reject it. So it's either reject or don't reject. There is no accept. Okay? So we can reject it. If, like on the car example earlier, the gas mileage, when we got a result that it was like, there's only a 0.1% chance that this is true, then we can reject it. We say, nope, not going to take, no, we're definitely not making any decisions based on that. We're going to reject that hypothesis. And anytime you get what kind of the rule of thumb here is, anytime you say you get a result that's less than 5% chance, then you can go ahead and reject it. But if you get a result that's anything more than 5%, then you are not going to reject it. So even if you get a result that's only 10% likely, you're still not, based on that, you're not going to reject the hypothesis. You're going to fail to, you're going to say, well, I don't know yet. I'm certainly not accepting it, but I'm not rejecting it either. All right. Sorry to belabor that point. Because your decision is based on a sample rather than the entire population, there is always the possibility you will make the wrong decision. In either case, you could make the wrong decision. You could reject it when you shouldn't have, or you could fail to reject it when you should have. And that's just because probability is not a certain thing. It's just it's what the word says. It's probably the case. For instance, you claim that a coin is not fair. To test your claim, you toss the coin 100 times and get 49 heads and 51 tails. You would probably agree that you do not have enough evidence to support your claim. Even so, it is possible that the coin is actually not fair and you had an unusual sample. But then you toss the coin 100 times and get 21 heads and 79 tails. It would be a rare occurrence to get 21 heads out of 100 tosses with a fair coin, so you probably have enough evidence to support your claim that the coin is not fair. However, you cannot be 100% sure. It's possible that the coin is fair and you just had an unusual sample then. So again, it's possible that you might just have an unusual sample. And then if that's the case, it's going to lead you oftentimes to the wrong decision, but not usually. Usually it leads you to the right decision. All right, letting P represent the proportion of heads, the claim that the coin is not fair can be written as the mathematical statement P does not equal 0.5. Its complement, the coin is fair, is written as P equals 0.5. So your null hypothesis and alternative hypothesis are what? You always put the one that has any kind of an equal in there as the null hypothesis, the H0. And you put the one that doesn't have any equal to on there as the alternative hypothesis. So in this case, you make the claim that the coin is not fair be the alternative hypothesis, P does not equal 0.5. And so you let the opposite of that, P does equal 0.5, be the null hypothesis. Remember, the only way to be absolutely certain of whether H0 is true or false is to test the entire population. Because your decision to reject H0 or to fail to reject H0 is based on a sample, you must accept the fact that your decision could be incorrect. You might reject a null hypothesis when it is actually true, or you might fail to reject a null hypothesis when it is actually false. These types of errors are summarized in this next definition. A type 1 error occurs if the null hypothesis is rejected when it is actually true. Perfect example of that kind of error would be the gas mileage example. The claim is that mu equals 50. Based on our sample, we are going to reject that claim. But there's a chance, a very, 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 very small chance, that our sample was just a very unusual sample, and it really is 50, and we should not have rejected it. That the claim really is true, but we rejected it, and we were wrong. That's a type 1 error. When you reject the null hypothesis, but you shouldn't have, it really is a true thing, then that's called a type 1 error. A type 2 error occurs if the null hypothesis is not rejected when it is actually false. So let me go back to that same example. Let's just say the claim was 50 miles per gallon, and our sample ended up with like 48 or 49. And so it was inside of that probability distribution to where we wouldn't reject it. Let's say maybe it was like there's a 25% chance that it really is true, so we wouldn't reject it. But maybe we got an unusual sample with that, and it really is false. That's a type 2 error. Okay, so here's a truth table of this variety. So when you don't reject H0, but H0 is true, we don't reject H0 and H0 is true, that's good. That's correct. H0 is true and you don't reject it, that's the correct decision. But if H0 is true and you do reject it, that's a type 1 error. If H0 is false and you don't reject it, that's a type 2 error. If H0 is false and you do reject it, that's good. That's a correct decision. You might want to stare at that chart until it makes sense. Hypothesis testing is sometimes compared to the legal system used in the United States. Under this system, these steps are used. 1. A carefully worded accusation is written. 2. The defendant is assumed innocent, H0, until proven guilty. The burden of proof lies with the prosecution. If the evidence is not strong enough, then there is no conviction. A not guilty verdict does not prove that a defendant is innocent, right? Not guilty does not mean he's actually innocent. It doesn't prove that he's innocent. It just means that it was not proven well enough that he was guilty to say that he was guilty. Number 3, the evidence needs to be conclusive beyond a reasonable doubt. The system assumes that more harm is done by convicting the innocent, which is a type 1 error, than by not convicting the guilty, which would be a type 2 error. That's really interesting, isn't it? So it's saying that it's better to make a type 2 error, which is to let a guilty person go free, than to make a type 1 error, which is to put an innocent person in jail or worse. All right. Both of them are serious errors, but our justice system says that the type 2 error is not as bad as the type 1 error. So you can stare at that chart until it makes sense as well. Identifying type 1 and type 2 errors. The USDA limit for salmonella contamination for chicken is 20%. A meat inspector reports that the chicken produced by a company exceeds the USDA limit. You perform a hypothesis test to determine whether the meat inspector's claim is true. When will a type 1 or type 2 error occur? Which error is more serious? Okay, let's figure out the claim. The meat inspector has a claim. His claim is that it exceeds the limit being 20%. So the claim is that P, because it's a proportion, it's not a mean, a mu, it's a proportion, it's a percentage. The claim is that P is greater than 20%. So because it doesn't have an equality, we make that the HA. The claim is P is greater than 0.2. So H0 is the opposite of that. P is less than or equal to 0.2. So a type 1 error is when we reject, let me make sure I'm right about that. So a type 1 error is when we reject a true H0. So it would be, if this is really true, the proportion is really less than 20%, but we reject that. We say, well, no, don't believe that. The claim is true. It's higher than 20%. So that would be a type 1 error. A type 2 error would be when we fail to reject a false H0. So if this was false, P is less than 0.2. That's really not true. P is not less than 0.2, less than or equal to 0.2. And we fail to reject that. That's type 2 error. So we're saying it could really be less than 0.2 based on the data. We can't say that it is not less than 0.2. And so the more serious error, seems to me, would be the type 2 error, would be to say that we fail to reject this H0, right? P is less than or equal to 0.2. It means that chicken is okay. And we fail to reject that possibility that the chicken is okay. We say, okay, it could be. The chicken might be okay. That's a more serious error because it's going to introduce contaminated chicken into the population, which is going to make people sick or worse. That's a more serious error than the type 1 error, which would be to reject this, even though it might be true. To say that it might be true that the chicken is okay, but we reject that and say, no, the chicken's bad. That would be an error also, but it wouldn't be as serious of an error. It wouldn't be as serious of an error to throw away good chicken than it would be to feed people bad chicken. I hope that makes sense. You will reject the null hypothesis when the sample statistic from the sampling distribution is unusual. You have already identified unusual events to be those that occur with a probability of 0.05 or less. When statistical tests are used, an unusual event is sometimes required to have a probability of 0.1 or less, or 0.05 or less, or 0.01 or less. And it depends on the seriousness, right? The seriousness of the kinds of errors that we make. Because there is a variation from sample to sample, there is always a possibility that you will reject the null hypothesis when it is actually true. In other words, although the null hypothesis is true, your sample statistic is determined to be an unusual event in the sampling distribution. You can decrease the probability of this happening by lowering the level of significance. In a hypothesis test, the level of significance is your maximum allowable probability of making a type 1 error. It is denoted by alpha, the lowercase Greek letter alpha. So that symbol right there. The probability of a type 2 error is denoted by beta, the lowercase Greek letter beta, that symbol. By setting the level of significance at a small value, you are saying that you want the probability of rejecting a true null hypothesis to be small. So rejecting a true null hypothesis, that's a type 1 error, you want that to be really small if a type 1 error is the more serious kind of error. So you would set the alpha level to be, real small, like maybe 0.01 instead of 0.05 or 0.1. If a type 1 error is not that serious, or if a type 2 error is the more serious error, maybe you make alpha be a little higher. Maybe you can make it be 0.1 instead of 0.05. 0.05 is kind of the middle of the road, the most common one. Statistical tests and p-values. After stating the null and alternative hypotheses and specifying the level of significance, the next step in a hypothesis test is to obtain a random sample from a population and calculate the sample statistic, such as X bar, that's the sample mean, p hat, which is the sample proportion, or S squared, which is the sample variance, corresponding to the parameter in the null hypothesis, which is mu, which is the population mean, p, which is the population proportion, or sigma squared, which is the population variance. This sample statistic is called the test statistic. It's hard to say. With the assumption that the null hypothesis is true, the test statistic is then converted to a standardized test statistic such as z, t, or chi squared. That's the Greek letter chi. The standardized test statistic is used in making the decision about the null hypothesis. In this chapter, you will learn about several one-sample statistical tests. The table shows the relationships between population parameters and their corresponding test statistics and standardized test statistics. So when we're testing out mu, and we're finding the sample mean, we're going to use the z or the t test based on what we learned back in chapter 6. Remember, we use z when the population standard deviation is known, or we use t when the population standard deviation is not known. For the population parameter p meaning a proportion, we're going to use a z-test, which is going to be explained in section 7.4 of this chapter. If we're trying to find sigma squared, the population variance, then we're going to use what's called a chi-squared test, which is section 7.5 of this unit. We may not get to that, we'll see. One way to decide whether to reject the null hypothesis is to determine whether the probability of obtaining the standardized test statistic, or one that is more extreme, is less than the level of significance. If the null hypothesis is true, then a p-value or probability value of a hypothesis test is the probability of obtaining a sample statistic with the value as extreme or more extreme than the one determined from the sample data. So that's going back to the first thing I did with you in this video when I did the example on the calculator about the gas mileage. That was finding the p-value for that null hypothesis being true or not. Moving on. The p-value of a hypothesis test depends on the nature of the test. There are 3 types of hypothesis tests: left-tailed, right-tailed, and two-tailed. The type of test depends on the location of the region of the sampling distribution that favors a rejection of H0. This region is indicated by the alternative hypothesis. So hopefully I can explain this to you well. So let's say our H0 was P or mu or something being equal to some value, and so our HA is P is not equal to that value. So we're saying here's the value K. And so since it's an equality, I'm saying it's okay to be anywhere in here, but it's not okay to be anywhere out here. All right, that since we're centering around K, that is called a two-tailed test. Two-tailed test. Or you might call it a center test, because you have a center. All right, if H naught were something like P is less than or equal to K, and so HA was P is greater than K, then that would look like this. Okay, here's K. We're saying anything over here is good. In fact, we could even go over here some and say everything over there, we won't be able to reject it. But anything, there comes a point where we get into the bad part over here, where we would want to have to reject it. That's called a right tail test. And then connected to that, what if H naught was something like P or mu or whatever is greater than or equal to K, and so HA would have to be P is less than K. Okay, here's K. And so we're saying everything over here means it's true. But also if we go a certain amount even past this, we won't be able to reject it. But there comes a point over here where we would reject it because it would be so extreme away from H naught. This is called a left tail test. So you can read this, pause this if you need to read this stuff. This is pretty much what I just taught you, what I was just showing. But if you want to read it from the book, feel free to read that. The smaller the p-value of the test, the more evidence there is to reject the null hypothesis. A very small p-value indicates an unusual event. Remember, however, that even a very low p-value does not constitute proof or absolute proof that the null hypothesis is false, only that it is probably false. Example 3. Identifying the nature of a hypothesis test. For each claim, state H naught and HA in words and symbols. Then determine whether the hypothesis test is a left-tailed test, right-tailed test, or two-tailed test. Sketch a normal sampling distribution and shade the area for the p-value. All right, number 1, a school publicizes that the proportion of its students who are involved in at least one curricular activity is 61%. So mu equals, sorry, not mu, since it's a proportion, it's a percent. P equals 0.61 is the claim. That's the claim. And since that involves an equality in some way, that's going to be H naught. So then HA will be the opposite of that. What's the opposite of that? P does not equal 0.61. So if we draw that, here's 0.61, and we got to be at least so far away in order to reject it. So all that right there is okay, but anything out here is not okay. So that would be a two-tailed test, or we might even call it a center test. And so the p-value would correspond to that red area that I shaded right there. The p-value would correspond to those areas under the curve. All right, let's do number 2. A car dealership announces that the mean time for an oil change is less than 15 minutes. So number 2, that was number 1. 2, mu is less than 15. So that's got to be HA, since it's doesn't have an equality symbol involved in it. So H naught would be the opposite of that, which is mu is greater than or equal to 15. Okay, so H naught is greater than or equal to, so everything over here is true, supports that it's true, and even something over here wouldn't allow us to reject it, but there would come a point over here where we would reject it. And so this would be what? A left tail test, and this would be the p-value right there in that red area. Number 3, the company advertises that the mean life of its furnaces is more than 18 years. So mu, make some more room. Mu is greater than 18 would be the claim. And I should have said over here that this is the claim. This is the claim. And since that doesn't have an equality sign, then that's got to be HA. So H naught will be the opposite of that, which is mu is less than or equal to 18. So here's my thing. Here's the 18. Everything this way supports H naught, and even so far over here would not allow us to reject H naught, but there would come a point over there where we would be able to reject H naught. And so that's the p-value of this being called a right tail test. All right, you may want to read the book's solution to this. Feel free to read that. All right, moving on. Making a decision and interpreting the decision. To conclude a hypothesis test, you make a decision and interpret that decision. For any hypothesis test, there are 2 possible outcomes. 1, reject the null hypothesis, or 2, fail to reject the null hypothesis. To use a p-value to make a decision in a hypothesis test, compare the p-value with alpha. And remember, alpha is something that is determined at the beginning by you or by someone else, depending on, and usually that depends on how serious the kinds of errors could be. If p is less than or equal to alpha, then reject H naught. If p is greater than alpha, then fail to reject H naught. Notice again, let me stress it again, there in no circumstances are you saying you accept H naught. You're just either saying reject it or fail to reject it. Reject it or don't reject it. No accept. No accept. Failing to reject the null hypothesis does not mean that you have accepted the null hypothesis as true. It simply means that there is not enough evidence to reject the null hypothesis. To support a claim, state it so that it becomes the alternative hypothesis. All right, that's important. If you want to support a claim, state the claim as the null. To support a claim, state it so that it becomes the alternative hypothesis. If your goal is to support some claim, then you want the claim to be the HA, not the H naught. To reject the claim, if that's your goal, if your goal is to reject the claim, so it depends on if you're the prosecution or if you're the defense. To reject the claim, state it so that it becomes the null hypothesis. If your goal is to reject the claim, then you need to make the claim become H naught, not HA. Okay? This table summarizes that. Reject H naught. The claim is H naught. There is enough evidence to reject the claim. All right, if the claim is H naught, but you fail to reject H naught, there is not enough evidence to reject the claim. Okay? If the claim is HA, and you reject H naught, there is not enough evidence to support the claim. If the claim is HA and you fail to reject H naught, there is not enough evidence. I don't know if I said it right earlier, but there is enough evidence to support the claim would be on that one. And on this one, there is not enough evidence to support the claim. So you're never saying there is evidence to accept the claim. There is either enough evidence to reject it, there may be enough evidence to support it, or there may be not enough evidence to reject it, or not enough evidence to support it. You're going to have to think about that for a while, I think, to understand it. I know I have to go back and look and think about what those things mean myself. All right. Example 4. You perform a hypothesis test for each claim. How should you interpret your decision if you reject H0? What about if you fail to reject H0? So the claim, H0. School publicizes that the proportion of its students who are involved in at least one curricular activity is 61%. The claim is represented by H0. If you reject H0, then you should conclude there is enough evidence to reject the school's claim that the proportion of students who are involved in at least one extracurricular activity is 61%. Again, since the claim becomes H0, we can either say there is enough evidence to reject it, or you can say there is not enough evidence to reject it. That's all those are the only two things you can really say. You can either say that there's enough evidence to reject that claim, or you can say there is not enough evidence to reject that claim. That's all you can say. All right. So what if the claim was the alternative hypothesis? The car dealership announces that the mean time for an oil change is less than 15 minutes. In that case, the claim is the alternative, and so we are either rejecting not that, but the other. We're rejecting the null hypothesis, which would be that it is greater than or equal to 15 minutes. So we would say either there's enough evidence to reject H0, which means there's enough evidence to support HA. There's enough evidence to support the claim. Or you could say there's not enough evidence to reject H0. And so we could say there's not enough evidence to support the claim then. So in that case, we're not rejecting the claim. We're either supporting the claim or not supporting the claim. So you see how the wording works there? And so that's why you want to, this statement is pretty important, these two sentences, how you want to state it based on your goal. Okay, here is a table, not a table, but just a summarization of the steps for hypothesis testing. Feel free to read this. Pause this at any point and read those steps if you would like. In step 4 above, the figure shows a right-tailed test. However, the same basic steps also apply to left-tailed and two-tailed tests. Strategies for hypothesis testing. In a courtroom, the strategy used by an attorney depends on whether the attorney is representing the defense or the prosecution. In a similar way, the strategy that you will use in hypothesis testing should depend on whether you are trying to support or reject a claim. Remember that you cannot use a hypothesis test to support your claim when your claim is the null hypothesis. So as a researcher, to perform a hypothesis test where the possible outcome will support a claim, word the claim so that it is the alternative hypothesis. So the alternative hypothesis, remember, does not need to have any equality in there. So that's important, whether or not you say less than or equal to, or just less than, or something like that. To perform a hypothesis test where the possible outcome will reject the claim, word it so that the claim is the null hypothesis. So you can word your claims or word your hypotheses based on your goal, and make sure you word them with either less than or equal to, or just less than, or greater than or equal to, or just greater than, or equal to or not equal to, in the way that you want it. Example 5, writing the hypotheses. A medical research team is investigating the benefits of a new surgical treatment. One of the claims is that the mean recovery time for patients after the new treatment is less than 96 hours. All right, so the mean recovery time, so mu is less than 96. That's the claim. So the other would be mu is greater than or equal to 96. So number 1 says, how would you write the null and alternative hypotheses when you are on the research team and want to support the claim? If you want to support the claim needs to be HA. So that's kind of what it's going to be naturally anyway. So if we want to support it, to support the claim, this is what we'll do. However, if we want to, how would you write the null and alternative hypothesis when you're on an opposing team and want to reject the claim? So if you have doubts about this claim and you want to test it and make sure you get this done right, and you want to give the best shot at rejecting it, then you want the claim to be the null hypothesis. So you need to take this and make it be H naught. How would you make that be H naught? You'd have to say mu, instead of just less than 96, you'd have to say mu is less than or equal to 96. Let that be H naught. And then let HA be mu is greater than 96. So you do this if you want to reject the claim, if that's what you're trying to see if it can be done. Okay, now that is finally it for section 7.1. See you again in another video.